Hello everyone, my name is Peter Lyons, and this is the first lab for Physics 2211, which pertains to Newton's second law. In this lab, I observed the motion of an object that is moving at the same speed without changing direction. I captured a video of the motion and then analyzed the video using Tracker to extract the object's position and time data. I then constructed a computational model that accurately describes my observations based on physics principles, which, in this case, is Newton's second law, or, equivalently, the momentum principle. I then compared my model to my observations by plotting both the observed position versus time from the analysis of my video and the predicted position versus time from my computational model on the same graph. So, Newton's second law. Newton's second law is what we can use to predict where an object will go based on its current velocity and the forces acting upon it. Two equations come from this fundamental principle, which is the equation for new velocity and new position. Newton's second law equations include the velocity equation and the position equation. The velocity equation says that Vf equals Vi plus F net over m delta t. Breaking this down, it says that the final velocity of an object is equal to the initial velocity of an object plus the net force divided by the mass times the change in time. The second equation, Pf equals Pi plus V average delta t, says that the final position of an object can be found by adding the initial position of the object plus the product of the average velocity and the change in time. Now, to our tracker analysis. Here I have a video of my friend Earl pushing a basketball on my command. I have set a calibration stick on the basketball and set it equal to 0.2344 meters, which is the diameter of the basketball. I set the basketball to be at the origin. Now, after tracking the data, you can see that the ball goes in the negative x direction, which means that it has a negative velocity. Looking at the graph in the top right, you can see that the graph has a negative slope, which also means that it has a negative velocity. Moving on to the computer model, here I have the code versions of both of the equations for Newton's second law. Ball.vel equals ball.vel plus Fnet divided by ball.m times delta t. And ball.pos equals ball.pos plus ball.vel times delta t. The initial properties for my system are the mass, which is 0.635 kilograms, but keep in mind that this does not matter because our net force is 0. Our position is set at 0, or the origin. Velocity of our ball is set to be negative 1.1347 meters a second for the x-axis, which means that it's going 1.1347 meters a second in the negative x direction. Our t is equal to 0, which is where we start our clock. Running the computer model, you can see to the window on the left is a visual representation of the motion of the ball. And on the bottom right, here's a graph showing the object's position over time. Putting all this data into Excel, you can see that the tracker data is modeled by the computer model almost perfectly, if a little underestimated by it. More things to consider from this experiment are, what if I flipped the axes? Say I pushed the ball from the left to the right instead of from the right to the left. Well, that means that the velocity of the ball would be in the positive x direction instead of the negative x direction. And the graph would be in positive upward sloping line rather than a negative downward sloping line. Another thing to consider are, how do we know that all of the forces acting upon the ball add up to 0? Well, to answer that question, we don't. Friction could be acting upon the ball, gravity could be acting upon the ball, even maybe some sort of a drag force as the ball is being pushed across the table. We don't know 100% that the forces on the ball added up to 0. We just assume this for this experiment.